demo today are reaction patterns, okay? So as we're talking about reactions, the big thing that affects why something behaves the way it does is because of these valence electrons. That when things have the same number of valence electrons, they react in a similar way. So everything in the first column had one valence electron, and we saw that similar type of reaction behavior. The thing that we need to recognize here that we're going to really focus on the most is it's really about those valence electrons, okay? Are really where we're focused in the end. And then what we get are similar valence electrons within a group result in similar properties. So things that are up and down to each other are a lot more similar than one next door. And that's why we call them a group or a family in the end. Okay, so the reason why atoms do what they do is they're all trying to achieve this full octet. What is the term, why do we use the term octet? Because it goes to 8, right? That they all want 8, they all want a full, stable outer shell. That is what I imagine as the goal of the life of an atom, is they want to get 8 valence electrons. And once they do, they are stable, they are complete, and they're good, right? This is why the noble gases don't react, is because they're already good the way they are. They don't need another element to make them happy.
Do they
right?
ever reoccupate?
Okay, so as a review, the number of electrons we can find by looking at the column numbers. So you might want to write these above that little periodic table there, right? That everything in the first column has 1 valence electron, 2, skip the D block because those ones are going in the inner levels, and then 3, 4, 5, 6, 7, 8. So a really easy pattern on the periodic table to find how many valence electrons something has. Now something we got to be careful with when we talk about this full idea. So we say an atom wants to have a full outer shell. Okay? The thing you got to remember is an atom can get full in 2 ways. It can get full by putting in more electrons, but then also how?
By losing the...
Also by losing, because technically if it loses the whole outer shell, then the inner shell is full. Okay, this also leads us into the idea of ions, where ions are created when they gain or lose electrons and they create something that is charged. So on that same periodic table, you might want to, as a review, write above the different charges that the columns form. Nathan, did you have something?
Isn't helium the exception to the U10 plus it's an
Yes, ooh, good point, right? Because how many electrons does helium actually have?
Those.
Just 2, but is 2 considered full for helium? Yes. Yeah, so that's where in saying it's a full octet isn't always true. We're really just looking for a full shell. So yeah, good point. Okay, let's review really quick. What does it mean when I say it's a +1 charge?
Because it loses 1 electron.
Good, so that means that you, Clark?
Yep.
So a positive charge means it has given the 1 electron it had away. So when I say you're eating potassium in a banana, you're eating this, not this. Such a subtle difference in how we write it, but down at the molecular level, what's the difference between these 2 things?
Wait, what's the S mean?
I'm just saying it's a solid.
Oh, okay.
One melts your mouth and the other tastes good.
So what we see, yeah, one of these, this will light your tongue on fire. This one helps you not get muscle cramps. Okay, and then why? What's the difference of
That
these
one's
2?
happy, so it won't react.
Yeah, this one's now stable. It has its 8. It doesn't need to react with your tongue because it already has its 8 valence electrons.
Okay, so
This
how...
one. Okay, so as we're looking at our trends, the main thing to focus on here, the way to visualize it, is kind of like a magnet. Okay, that inside an atom, protons in the nucleus attract the electrons out in the cloud. And that's going to be the main force we're focused on today, is this positive, negative attraction. Okay? Yeah. So when we look at this idea of positive and negatives, it goes down to a technical term known as Coulomb's law. Okay, this right here is the equation. We're not going to focus on using the equation. What I want you to know from it are these 2 things. Okay, that Coulomb's law tells us The more protons and electrons something has, the greater the attraction. I think of it as more positives, more negatives, the magnet is stronger. Okay? We also see a pattern, though, that when an atom is small in size, there's also more of an attraction.
But why?
Okay, so this one I think of as like in terms of distance. Okay? Is that the closer two magnets can get to each other, the stronger the force will be. So think of it if you had like a bunch of grapes that were like all magnets versus like a bunch of oranges, right? Who's going to hold tighter together if you pour them like in a box?
Grapes.
Can everyone see that? Why would the grapes hold tighter? Because there's going to be like less space in between them, right? Like a bowl of grapes versus a bowl of oranges, because they're smaller in size, there's greater proximity, so a greater attraction. Versus oranges, which would have bigger empty spaces where they just can't touch. Does that make sense? Okay. All right, so let's look. When I'm going down a family, what is the main thing that's changing in terms of this attraction? Okay, so if we're looking at our alkali metals again, okay, and I were to draw a picture here, lithium, I'm going to draw it down lower. Lithium is on the second row of the periodic table, which means it has 2 energy levels. When I jump down a row, that adds a whole new energy level. So sodium, like so, potassium, and the pattern continues. Okay? So as we go down a group, we see a greater distance from the nucleus because there's a new ring being added on. The greater distance results in a decrease of attraction. Okay? So as we're talking today, it's a little weird, but I'm going to use the analogy, okay, that we are going to be an atom. Okay, so visualize this with me here. So I am the nucleus of the atom, okay, and each row of you are my rings of electrons. Okay? So I'm looking at all of you. Who are my valence electrons?
Yeah, the back.
The back row right now, okay? Versus like if I was hydrogen, then you guys would be my valence because I only have one ring. Right? Everyone kind of see. So, not to make the rest of you feel bad,
I feel so bad.
okay? But as we talk today, the valence electrons are the ones that really matter. So congratulations, back row. You're the ones that matter today. The rest of you are already stable, so I guess that's a compliment, right?
Good stable measures.
Yeah. Okay, the inner electrons are stable. They just orbit. Really all we care about in chemistry are those valence ones. As you saw with configurations, those inner ones are just always the same, right? 1s2, 2s2, that pattern doesn't change. The ones that are varying are those outside ones as they try to gain stability, okay? All right, so something we need to look at, and this kind of hopefully will help answer Carolyn's question a little bit, okay, is as we're looking at the valence electrons, okay, because they're the ones that we're curious about, are they leaving, are they coming, because that's what affects whether it reacts, okay, we know that there is this force. All the electrons feel a pull from the nucleus, because the nucleus is positive, okay, but the valence electrons can't feel the full force. Okay, they can't feel the full love of the nucleus. So now why? Why does the back row, why do the valence electrons, why can't they feel my full love, my full attraction?
Because they're not as attractive.
They're not as attractive. Not quite, but good try. Any other thoughts? What's wrong? Why can't they feel that full force? Russell? So one is definitely the distance, right? That they're all the way back there.
Long distance relationship.
Long distance relationship, right? But what's the other problem? Okay, the rest of you are shielding the love of the nucleus from the valence electrons. So that's why even though if I'm cesium and I have a positive 55 nucleus, Russell doesn't feel that because there's 54 electrons taking that love away. There you go. Okay, so we get this idea of shielding. The inner electrons shield the valence electrons from feeling the full attraction. Does that kind of answer your question a little bit more, Carolyn? Okay. All right, so first trend, skipping this one for now. Oh, horizontally, let's look first. Okay, so we look down a group. The main factor down a group is rings. We're adding more. When I go across a row, okay, as I go across this row, if this is the second row, the ring number isn't changing because they're all in the second row. So what is changing when I go from lithium to beryllium? What changes? Okay, so we have one more valence electron. What else do we have? And one more proton. So what did we talk about? When something has more protons and electrons, stronger force. So we actually see as we go across the periodic table, there's a greater attraction, which makes sense. If you look, and I go across, neon holds onto its electrons really, really, really tight. Doesn't want to let them go in relationship to lithium. Okay, so we see increased attraction as we go across due to the fact that we're adding more protons, but we're not adding any more rings. And so it doesn't decrease the distance. Okay, as we go to the left, they're held loosely. As you go to the right, they're held more tight. Okay? All right, so now let's apply those two things. Oh, here's kind of a summary. The general rule of thumb, if you want to put it in a diagonal line on your notes, is that up and to the right, things hold onto their electrons tighter. Okay, so on that little periodic table, if you want to draw a diagonal line, down here they're held loosely, and up there they're held tightly. So based off this diagonal pattern, who's going to be the hardest to rip an electron away from? Helium. You're never getting an electron away from helium. Ever. Right? And who's just going to like let its electron go all the time? Francium. Like radius, aka the size of an atom. Okay? Just like if you think of a radius of the circle, that's really what we're measuring. Is we're measuring from the center of the nucleus to the outside electron orbital. Okay? So atomic radius refers to size. So the goal here is after today is in a comparison thing, you can tell me between calcium and barium, who is bigger? Okay? I don't want you to memorize the values of them. But based off the patterns, you should be able to tell me which atoms are the biggest and which ones are the smallest. Okay? All right, so first off, so here's our pattern. What do you see happening? As I look at this diagram, a period means a row. So which direction is it increasing, left or to the right? Good, so it increases as I go to the left in a period.
Why?
So now let's talk about why.
That's what it does on the graph.
Yes, it also matches up on your graph. We talked more about that last time for those that were gone. But so why? Okay, ready? Think about this with me, everyone. Why do atoms get bigger as I go this way? Or if it's easier to think about, why are they getting smaller that way? All right, everyone listen to Clark here. What do you think?
We were just talking about how they get looser as they go down, and so, to the left. So those are the most reactive. So.
Yes. Okay, so everyone on this row has 2 rings. The ring number isn't changing. But what happens is that the atoms down here, okay, don't pull as tightly, because there's only one little valence electron out there. don't pull as tightly on it as the ones over here, because they have all those little magnets. They're all getting pulled in, which decreases the ring size. Well, so now what we gotta look at, okay, so now let's look up and down, okay? So what's the trend that we see? Is it increasing to the top or to the bottom? Bottom, right? So the pattern increases as we go to the bottom of a group. So now once again, what is the reason why? Why do they get bigger as I go down? What's happening?
More shells.
Now it's more shells. Yep. Atoms just get bigger because it's a whole new ring. Which if you notice, okay, focus back up front up with me here. What has a greater effect? Going across or going down? Yeah, going down, the circle size changes a lot more than simply going across. Due to the fact that going across is simply pulling the ring in a little more or a little less, going down is adding a new ring onto the atom. 8 is known as ionization energy. Okay? So what ionization energy is, it's the energy required to remove an electron from a neutral atom. Okay, so in our analogy, ionization energy would be how much energy it takes for somebody to come in here and steal Sophia from us. Sorry, Sophia. Because she's a valence electron, right? If it takes a lot of energy for them to do that, then that's a high ionization energy. If it doesn't take much energy, then that's a low.
Yeah.
Okay? So let's talk about the trend. Okay? So according to my diagram, here's our key, right? Where the blue means a lower ionization energy and a red means a higher. So once again, we have exceptions, but focus on the big picture. Going across a period, which way is it increasing? Is it increase to the left or to the right?
Right.
To the right. Right? Generally, we see that there's more red and oranges as we go to the right. Okay? All right, what about our group pattern? Is it increasing up or down?
Up.
Good. Generally, it's increasing as we go up. There's more red near the top. So now let's talk about the 2 reasons of why. Okay? Going across, why is it easier to take an electron away from boron than it is from fluorine?
Because the pull is not as strong.
Fluorine has a much stronger attraction to its electrons, force, than boron does. Because it has, what, 1, 2, 3, 4 more protons pulling them in. Right? So going across, we see that the greater the attraction, the higher the ionization energy. Right? It's going to take a lot of energy for somebody to come and take away fluorine's electrons. Okay, so now let's look in a group. Why is it harder to take away an electron from oxygen than it is from tellurium? What changes there, Annalie?
So the attraction energy is less because it's getting, like, the shells are getting bigger, like we talked about with, like, Wednesday.
Good. Yeah, so like tellurium, right? If I was tellurium, somebody comes in and tries to steal Annalie. I'm the nucleus. She's kind of far away. You're all in the way. There's tables in the way. Sorry, they just take you. Right? But if somebody comes, if I'm oxygen, somebody tries to come and steal Julie, well, I'm right here. Right? The force is strong. I can stop them before they take her away. Right? So that smaller distance due to the ring size allows the force to be strong, meaning it would take a lot of energy to rip that electron off. Right? Okay. Questions on what ionization energy is? All right, we're going to stop there today. That's the bottom of the page, right?